Welcome back. We are going to take a few minutes to look at how Green's theorem, stuck in the plane, xy plane, can be extended to 3 dimensions fairly intuitively, I would say. The proofs of these 2 extensions are a little bit different because of all the number of components involved. We won't go through the proofs, but I want to talk about how the idea of Green's theorem can be extended into these 2 other theorems called Stoke's theorem and the Divergence theorem, which are heavily used in other disciplines. I want you to first imagine that you have a bubble wand, and we're going to blow a big bubble. Okay, so we first start out with this bubble wand, little circle. No, it doesn't have to be a circle, it's something, some shape. There we go. And here's our region inside. And we are going to, let me first stretch this a little bit so we can tilt it just slightly. Oh, that's not going to work. Okay, so let me back up. I'll just draw a separate circle for that independently. Here is our bubble wand. Our xy plane is slightly turned. Our curve, C is going around it. I'll label it down there so we can see it a little better. And we are going to blow through this bubble wand. I think we were holding it down at the bottom. Oops. We're holding it down at the bottom here, and we're going to blow a bubble. And as we blow, this soap film create a nice little bubble surface. And that surface connects down with our region, with our curve that hasn't changed. And so we can describe this curve as being the boundary of that surface. And what we're going to do is apply the circulation form of Green's theorem to this surface, treating that surface S as being the extension of the region A, where we were previously adding up all the little curls. Now when we add up the little curls, we're looking at these curls as they rotate counterclockwise on the surface. So over there, over here, over there, and in the back, like that. And we can think of that counterclockwise rotation as being oriented to the top or upper face of that surface. And we can describe each of those curls as being about a normal vector. n. Previously, all those normal vectors were just k hat. And you probably still have one somewhere up here that's close to k hat. But all the others have been tilted a little bit. Kind of think of them like porcupine quills sticking out around the porcupine's body. And so the curl that's being added up, that was being added up in the region, is now being added up along this surface. But it's still equal to the work done by the vector field F to move particles all the way around the curve that's bounding this surface. You can imagine that this surface has a gaping hole where the bubble wand is. And until that bubble film lets go of the wand and forms a bubble, that surface has an opening, and that is where Stokes' theorem applies. We have this surface that's not closed, a surface that has a boundary, so it's not closed, but the boundary itself is a closed curve. So a closed curve surrounding the hole that is the opening for this surface before the bubble film forms the bubble. And as there's an interesting little backstory behind the Stokes theorem. I'll let you read into that later. Ironically, Stoke neither discovered nor proved the theorem we named after him. It was actually discovered by Lord Kelvin, or possibly others, chemists, Lord Kelvin, and then it was presented as a prize that basically said, here's a hard problem, I'll give money to whoever can prove it. And it wasn't until 6 years later that someone was able to prove it, Hermann Hinkel. So there you go. If you find a hard enough math problem and give other people money to solve it, you can have your name on it too, I suppose. So let's look at how the Green's theorem changes for this. Well, on the left side, nothing has changed. This is the integral over the closed curve of the field dotted with a direction of motion. That's our t hat direction. We still have that direction labeled. This is this vector right here is t hat. That vector right there, t hat. And the field itself, I'm not drawing the field because that's too many arrows, but there's some field that's moving around this, it is creating some kind of movement around this surface. Often we think of this as like, you could think of it as like a wind velocity field blowing the bubble. That's kind of like that is an example of a vector field. You could think of this as gravitational field, conservative field. You could think of this as a magnetic field, an electric field, temperature gradient field. There are a number of different things that you can use to represent the field. They don't change. They don't impact necessarily the surface or the curve. The surface and the curve are always independent of the field. The measurements we are taking is how much they line up, how much they align with the field in terms of the movement around the curve. That's the work done, or circulation, work done all the way around. Circulation of the field is measured by the orientation and alignment of this wand, the bounding curve. On the other side, we had before the curl or cross product of F with del operator. That stayed the same, but now instead of a k hat and a dA, we have an n hat, which is the normal vector at any point on that surface, and a ds. And that ds represents a little patch of area on this curved surface. And we can use the columns of the Jacobian. This goes back to that surface integral we were working with before. We previously looked at a scalar surface integral where the surface integral had the magnitude of this cross product. But if you multiply by the normal vector, which is this cross product, divided by its magnitude, then you can write the normal vector times ds equal to the cross product of the two Jacobians in the directions of our surface. You can think of the u and v direction. We find the changes change in terms of those directions, cross them together, and we get our normal vector. And scale it back by the magnitude, which is the area of that patch. You think of it, the cost of transforming to these new variables. This is very similar to how we had, well, let's scroll up a little bit and grab it real quick. The flux, sorry, not the flux, the circulation form. I'll just move these pieces out of the way. There we go. Okay, so the left-hand side hasn't changed at all. The right-hand side has just changed the normal vector, which is no longer the z-axis, but some other direction, defined by the Jacobian, the columns of the Jacobian matrix. And instead of dA, we have that little patch of area, ds, which together can be expanded as du dv times the cost. Here, I can rewrite this fully out. That inside. The normal vector is a unit vector. That's our unit vector, normal, pointing outward, and then the ds pays a cost. You can kind of think of like a Jacobian, but it's actually the magnitude of the cross product of two columns of the Jacobian matrix. So it's not quite the determinant because we're working in 2 dimensions instead of 3 dimensions, times du dv, or rather dv du is a standard form. Writing that, either way is fine. Either orientation is fine. So that describes the components we would extract out. In general, it's quite complicated, but we saw an example with the sphere, how we can simplify that down. Or we will see, we can look later at examples of like the cylinder where it can simplify down really nicely. But Cartesian, the natural way of describing things, does lead us to some fairly complicated descriptions of these components. And that's what, I mean, that's not unsurprising when you take a flat film on a bubble wand and you blow a bubble that's just this strange shape. Of course it's going to get complicated. The math gets complicated. What's amazing is that there's some order in that chaos, that you'd have this bubble film that you're blowing into a bubble, and the moment before the bubble forms, you have a way of describing the normal vector at every point on that surface, and the area patch, and the cost of transforming from the original area that's flat to the area patch that's stretched on that surface. That is amazing. Not that it's complicated, that there's some semblance of order in all of this, and that it directly relates to this 2-dimensional form of Green's theorem. So yes, we give credit to Stoke for and Lord Kelvin for figuring out this thing was true, but we give a lot of kudos and credit to Heinrich Henkel for proving this. This is a pretty crazy idea and complicated in extending it in general. Now, what happens when that bubble actually forms from the surface that is extending from this bubble wand? Well, at that moment, the surface becomes closed. And we no longer have a bounding curve of the surface, but the surface itself becomes a bounding surface. And that leads us to the divergence theorem. So I'm going to clear this up and move on to the second form of Green's theorem, which I'll copy from above here. Oh, and note, if f is conservative, then its curl is 0, because we've shown that the cross product of the del operator and a gradient is 0. You can think of those two as being parallel vectors, which says no work is done over a closed curve, which is identically equal, which is agreeing with the fundamental theorem of line integrals. So if the curl is 0, then we are integrating all along around a conservative vector field and we get 0. The net curl is 0. Actually, here, every curl is 0 when it's conservative. So let's talk about the divergence theorem. So I'll quickly paste in the Green's theorem version and come back up here a little bit, give us some space to talk, discuss it. What we're going to imagine in this case is, instead of having a soap film that we're blowing into a bubble, we start out with a deflated balloon flat on the ground. And what we're seeing is just a projection of that balloon surface on the ground. And so it looks like a flat region with a closed curve around it. So let's imagine that. Here is our region. Here is our curve. C surrounding it. Now what we're going to do is blow the balloon, inflate the balloon really, right? Blow into the balloon. And that will give us oh, sorry, that's weird. Think of this as the end we tie together. And instead of being a region, we now have a domain. And on that domain, we have a surface S. And it has an outer surface and an inner surface. And because of that, we say it's oriented. And then we tie off the end of the balloon, that's that part right over here, to make sure that the surface fully encloses that balloon domain. And we can move that balloon through space and change its position, orientation, moving around, but the surface will always be closed around it. And the outer part of the surface will always be outer, and the inner part of the surface will always be inner, so that orientation stays the same. And that's the extension of a simple closed curve. Now, the piecewise continuous part will make the surface have patches that have continuous, have parts that can be differentiable in multiple directions. So you can make that surface, basically think of it as a patchwork quilt, where each patch is a plane that you can define functions that are differentiable on. Now, the region had to be simple and had to be connected and simply connected, which means that the domain has to be connected and simply connected. What does that mean if your region had a hole in it, though? Well, previously, we talked about cutting in surgically to get to that hole. In terms of a domain, that means that our balloon can have a little pocket inside of it. It has to be completely surrounded. So there might be some little pocket. Oops. Some little pocket inside, like a little air bubble inside the, well, or a liquid bubble, something inside that balloon. And it has to be completely surrounded so that the surface has a definitive outer and inner part. In this case, the surface orientation will flip. The outer part of the surface will point away or outside. On the outer part of the surface over here has normals that are pointed away, whereas the surface on the interior will have normals that are pointed inside. Just like our original curve had normals that are pointing outside on the exterior and inside in the interior, we can relate that same idea into 3 dimensions. Okay, so let's see how this idea connects to Green's theorem. First, I will mention that there are a lot of mathematicians involved in the discovery and proof of this divergence theorem. It was named after Gauss, who rediscovered it famously in 1813, though it had been discovered nearly 50 years before that. In 1762 by Joseph Louis Lagrange, who, like his mentor, Leonhard Euler, sometimes left personal discoveries unpublished, or at least didn't push for recognition. He published so much, just like Euler had, that sometimes he just did stuff for fun. And so Friedrich Gauss, a famous mathematician who was a savant at an early age, famously rediscovered this in 1813. And it wasn't until a Russian mathematician in 1826 that it was fully proven in its general form, Ostrogradsky. So it's sometimes called the Ostrogradsky theorem, but that's not as widely used. Often it's just called the divergence theorem for the terms used. So let's go down and look at how the mathematics bring order to this geometric idea. So we have an oriented surface S that encloses a connected and simply connected domain, one piece, no holes, or if there are holes, we just surgically cut into them to preserve a single boundary around it. And let F be some vector field surrounding it that has continuous first partial derivatives. And then the flux outward across the boundary surface along or aligned with the normal vectors. These are the normal vectors. Then the flux outward aligned with the normal surface, across normal vectors across the surface, is the macroscopic sum or net version of the infinitesimal fluxes around little bubbles of outward from little bubbles around every point, which we call the divergence at that point, computed by the dot product of our gel operator and our vector field. And so we take Green's theorem, which says we're integrating along a curved surface of the alignment of our vector field with the normal vectors, n hat, as we integrate along the arc length, along our path. That left-hand side turns into the double integral around a double integral over the surface S. And this actually should have a circle through it. Doesn't have it in the book, so I didn't mention it here, and it's kind of hard to typeset. There it is. No, it's close enough. So it's a closed surface integral, an integral over the entire surface of this field that has continuous first partials. Again, if there are places where the partials are not continuous or they don't exist, we have to create little bubbles, like over here. And then it's dotted with n, the normal vector. That's what we have over on this left-hand side. Sorry, right-hand side here. And then it's multiplied by, instead of d little s, it's d capital S. So instead of integrating over little pieces of length, the arc length, ds, we're integrating over little patches of little patches of area we call little patches of the surface area. And ds again has that same form as we saw with the Stoke's theorem. It's the magnitude of the cross product between two columns of the Jacobian corresponding to the two variables that describe the surface at that point. And then when we multiply it by the normal vector, which is that cross product divided by its magnitude, the magnitudes cancel out. We've seen this a lot of times with the magnitude of the velocity vector within the unit tangent vector. That's canceling out. And so again, we get a vector, a normal vector, multiplying by the du dv or dv du. Either order is fine. So that's the left. The right-hand side starts out as being the double integral over the region of the divergence of the field at every single point. So when we have this flattened, deflated balloon, we're integrating the divergence two-dimensionally out of each point. You can think of that in purple. Divergence at each point. How much is it pushing away? And then this turns, that is integrated over the region, dA. This turns into the triple integral over the domain of the divergence at every single point in that domain. So it hasn't really changed. It's just grown up from 2 dimensions to 3 dimensions. And we're adding up all those little divergences, little pockets of flux. And if we add them all up over the entire domain, they equal the net flux across the surface. Okay, so that here represents the 2 extensions of Green's theorem. I will say one more thing about divergence theorem, an example to kind of see how these ideas are connected together. One is that if F is a conservative field, something interesting happens. If F is conservative, then the divergence of our field is the Laplacian of the potential surface. So there's our Laplacian is just hanging out, waiting to be activated if we have a conservative field. And we're told that the sum of the Laplacian over the entire domain is equal to the gradient of the gradient vector dotted with a normal. So how much the gradient aligns with the normal vector out of the surface or on the surface is equal to the sum of the Laplacian at every single point in the interior. So Laplacian, in some sense, represents the divergence of the vector field when that vector field is conservative. So that's a good thing to remember. The Laplacian, kind of hiding back there, we saw that back with the gradient and extensions from it with the chain rule, is always there. It is a divergence for the special case when the field is conservative. And again, the Laplacian is the sum of the second, in Cartesian, is the sum of the second partial derivatives. So for 3 dimensions, the Laplacian is p sub xx plus p sub yy plus p sub cz. Okay, so now I want to end with an example of how we can derive an equation to model the flow of heat from a domain, a solid, based upon this divergence theorem. So I want you to imagine that this balloon that we inflated, even perhaps it's a little nugget inside, this balloon is a solid body. And we want to measure how much heat is flowing out of that body. Well, to do that, we can capture the amount of heat that flows perpendicular to the surface. And the reason why that's helpful is because that will give us that if we capture how much heat is flowing out of the surface, then we can equate to how much heat is being lost inside the solid. And so we can do some accounting here to balance what we're measuring on the surface to what could be measured in the interior. So I'm going to clear my drawings. And let's scroll down to look at some of the assumptions of this model. So if we want to derive the equation for the flow of heat, we first will assume that the body is uniform. We've seen that idea with a constant density rho for measuring center of mass. It's a uniform solid. We also want to think of it in terms of a constant specific heat in terms of the material properties of that solid. And then the heat of this uniform body is proportional to the integral of the temperature throughout the solid domain. It just means that if specific heat and density are constant, our heat is really just proportional to the temperature at each point. Now, heat is a measurement of energy in a sense, and so temperature and heat are not quite the same thing, but when the body is uniform, we can relate them directly by adding up the temperature over the entire domain. Okay, the second assumption is that heat flows opposite the temperature gradient. Now, this is a classic assumption that we see verified in nature around us. This is how the gravitational vector field works. It pulls objects in the direction opposite of the gradient of the gravitational potential. It pulls things in, even though the gravitational potential is getting greater and greater as we go out. Heat also will flow opposite the direction of the temperature gradient. And so we can set up this temperature gradient and negate it to get a direction of flow out of the surface to get flux. So we can compute the net flux of our heat by relating it to the negative gradient of the temperature. On the other side, we just have the heat loss, the change in heat that is negative, added up over the entire sorry. We don't have to, we could think of heat as a total heat for our region, so we don't have to integrate it. We will integrate it when we translate that into temperature. And so we can use this idea to set up our integration forms, and then we can derive the famous heat equation. This is one of the top 3 most famous partial differential equations for describing relationships, not just heat, but we're talking about like stock markets, we're talking diffusion of chemicals in the air. This heat model is so widely used, it's amazing. And it says that the change in temperature is proportional to the Laplacian of that temperature surface or temperature function. So let's go through these steps. First, let me modify that, correct this a little better. First, we have the change, the negative change in the heat as being equal to the flux of this heat flow out, where the heat flow out is negatively proportional to the gradient of the temperature. And then, since heat is the triple integral of T, Cp, we can do a little bit of swapping of our derivative. Notice here I've jumped through a few steps here. I'll rewrite that as a negative fraction d dt. Since heat is the integral of our temperature scaled by the specific heat in rho and density, we can factor that derivative out. But because this integral is in space and this derivative is in time, we can swap those two and bring that derivative inside to be just on the temperature and leave the negative out. On the right-hand side, we can also factor a constant out. And so now we have on one side a triple integral of a derivative in terms of t. So we can't use the fundamental theorem of calculus here. They're different differentials and derivatives. On the right-hand side, we have a double integral of a vector field dotted with n. And this is where the divergence theorem pops in. we are looking at the flux of a vector field over the surface or across the surface. And so we can use the divergence theorem to rewrite that as the divergence of this vector field, the del operator dotted with the gradient of the temperature profile. And dotting these two together can be rewritten as del squared. That is the Laplacian. That's the original form of the Laplacian operation, del dotted with del. And so we get del squared of t on the inside. On the outside, let's group our constants together. Dividing by negative c rho, we get a k, or I think it's a kappa actually for conductivity, thermal conductivity, kappa over c times rho. And this will separate us from two triple integrals. On one side, we're integrating the derivative of our temperature in terms of time. Other side, we're taking the Laplacian of our temperature. But these are the same integrals on either side. And since this model that we're deriving is true for any domain, then it means that the things on the inside of the integral must be equal for in all cases, and we can group that constant to be in the inside as well. And that allows us to extract out the things that are in the inside, the integrands on the two sides, to show that the change in time of our temperature is proportional to the Laplacian of that temperature. And I wanted to leave you with a little visual that I've enjoyed. This one is from YouTube in particular, but let me just let's move over to the Wikipedia page, and in this far right corner you can see an example plot of a interesting looking flat plate that is heated uniformly, and then the heat equation shows that the heat will diffuse out, and it diffuses out faster where the gradient is steepest. See, the gradient is really steep right there. It's 0 at that top edge, so there's no change originally. But as we get more and more change, the gradient increases and the heat flows outward proportional to the steepness of that heat profile. As you can see, the heat is maintaining more in the middle where the heat profile is leveled out. It's not as steep. So the gradient or the slope of the heat profile tells you how fast the heat flows out of a body. And this one, again, is just in 2 dimensions. So trying to graph a 3-dimensional heat flow of a body is complicated. We have to work with colors and in 3 dimensions and how the colors change to see the heat move out. And the yellow, of course, is kind of just the paper or some surface that's surrounding that plate as the heat flows out. Okay, that wraps up our extension of the 2 forms of the Green's theorem into 3 dimensions: Stoke's theorem, divergence theorem, and an example of how these ideas can be related to deriving models for physical phenomena, equations that describe things like heat, and then can be extended further to describe things like random walks, diffusion of gases, stock market prices, all kinds of things. So that allows us to wrap up. We'll talk later about how these key pieces are really just different perspectives and glimpses of that fundamental theorem of calculus that you first saw at the end of Calc 1. We're still going on and working with that fundamental theorem of calculus. It is that good. Okay, that's it for today.